Hello everybody, this is Derek France. Welcome to another video. This video focuses on the cyclohexane chair structures. And I wanted to begin this video by considering the 5 smallest cycloalkane rings, from cyclopropane on the top here to cycloheptane on the bottom. And the number in blue next to the rings is the strain energy of the entire system in kilocalories per mole as the unit. And what we can see here is that the cyclopropane and cyclobutane rings have substantial strain energy. The number in green is that value for strain energy divided by the number of CH2 groups in the molecule. So for cyclopropane, 27.6 divided by 3, because there are 3 CH2 groups, is 9.2. And so these values are present for all of these rings that we have here. So cyclopropane and cyclobutane are substantially strained. Cyclopentane and cycloheptane each have a little bit more than 6 kcals per mole of total strain energy. But what we can see is that there's something odd about cyclohexane. Just highlight this, make it big and bold. Something odd is occurring here with cyclohexane. There's 0 strain energy in this molecule, and then of course that would mean 0 kcals per mole of strain energy per CH2 as well. So how can cyclohexane be this perfect little strain-free molecule? Well, it turns out that the bond angles inside the cyclohexane ring, the bond angles here are not 120. This is not a hexagonal structure. The structure instead adopts what we call a chair structure. And here are some models. So here are models of the 2 chair structures. In cyclohexane itself, these are equivalent. But what you can see if you take a look here, it's kind of an up, down, structure that goes around the ring. It is completely strain-free, and the molecule has no eclipsing interactions of any kind. There's nothing in this molecule that's going to increase its energy due to any sort of unfavorable strain interaction. Now, there are strict rules on how we draw cyclohexane chair structures. I'm going to begin by showing you a really methodical way to draw it. With more experience, you can draw it in different ways as long as it looks the same way we're about to draw it here. So it's best to begin with a line that looks like that, a straight line that's diagonal, a little bit more left to right than it is top to bottom. And then draw a parallel line of equal distance, slightly offset to the left. Then what you're going to do is on the right side, draw a line that goes straight down here, and then connect it to the line that you had already drawn. We're going to do a similar thing on the other side here, draw a line like that, and then connect it like that. So that's how we draw a cyclohexane chair form. Now let's look at a couple really important features of this chair form. First of all, we don't draw it this way just to make your lives miserable. We draw it because it actually looks like the model up here. So the front is the bottom line. This bottom line right here is the front of the molecule, just as it is up here in our model. You can see that this bond goes over top of the bond in the back. So this is the front. Then by definition, this one here must be in the back. And that's the one right back here. That's this bond. So very importantly, that's how this structure looks. Let's consider on this side over here how we would draw it if we were to draw it in this orientation. It's quite similar. We draw a line like this, then another line, equally distant, equally long and just a little bit offset, but still parallel. Then we connect it like that, and we connect it like that. And this is actually a good demonstration of kind of a chair I don't like. I'm going to erase these lines over here and try to make that a little bit better. Drawing this digitally, I've found, is a little bit harder than drawing it on paper or on a board. That doesn't look much better. But we can live with it. I'm going to live with that as it is. So in this other chair form, the bottom bond right here is again in the front. as it is up here in the model. This bond then therefore must be in the back. And there it is right in the back. Now, let's decorate this molecule with the hydrogen atoms that are attached. There are very specific ways to put them in. So first of all, look at each of these carbon atoms up here. Each of these carbon atoms have one hydrogen atom that's in a vertical position, or almost nearly vertical position. And each of them have another hydrogen atom that's not in a vertical position, but it's also not in a horizontal position. We're going to talk about the nomenclature of that here in a moment. So let's begin with this carbon atom right here. If you can see where I'm pointing, this one on the far left top of the molecule, there's a hydrogen atom coming straight up. So let's draw that one in. And now we're just going to draw all of the vertical ones, all the vertical hydrogen atoms. In this atom here, it's going straight down. So when the carbon is pointing down, I think that's a good way to look at it. When you have a downward point where that carbon is located, the hydrogen points down. When you have an upward point, the hydrogen points upward. So I'm going to move this one here, then this one here, following our point rule that we just talked about, and also following how the molecule looks up there. Hydrogen there. And then in the back here, remember that is in the back, and look how that CH bond goes behind the CC bond in front. Just to be a little fancy, I'm going to put a bit of perspective there. Now let's do the same thing on this side. Well, let's not do that yet, actually. Let's put in the other hydrogen atoms. I'm going to use a different color. So if we start here on this carbon atom yet again, look at where that other hydrogen atom comes. It's parallel to this bond and this bond. So that means the hydrogen atom that comes out here will come down slightly, and it will be parallel to these two bonds. The hydrogen atom that comes off of this one will go up, and it will be parallel to that bond right there. The hydrogen atom coming off of this carbon that's going down will be coming out this way, parallel to this bond and this bond. The hydrogen atom coming off of this carbon will go up like that, parallel to that bond and that bond. The hydrogen atom coming off of this carbon will come down a bit. It'll be parallel to this bond and this bond. And then finally, the second hydrogen atom coming off of that carbon in the back will be going up in that direction, parallel to this bond and this bond. And there we have it, a cyclohexane structure. I'm going to move this, try to get my lasso. The program doesn't always let me get lassos for some reason, and it's not letting me do it now. So I have to use my mouse. Just going to move this over a little bit to give us space, and move that one over there. Okay, so now these different orientations of the molecules have different names. Just going to move this up a little bit higher, so we have some space to put some labels. Move that one up as well. Okay, here we are. So when you have a hydrogen atom or any other type of atom connected to the carbon of the cyclohexane that is either going straight up, like this one here, or straight down, like this one here, so all of the blue bonds are called axial. When a bond is going straight up or straight down, that position is called an axial position. All of these green lines are showing the other type of position, which is called equatorial. Like equator. So it's going around the molecule like an equator. But very importantly, no bond either in the cyclohexane itself or of any group coming off of the cyclohexane is horizontal. There is no horizontal line in this molecule. That's very important. Never draw a horizontal line on any molecule that's a chair structure. No horizontal lines. The equatorial positions are going to be parallel to one of the lines within, or two of the lines within the cyclohexane chair itself. Something else to consider here is that at each of these carbon atoms, there is one axial and one equatorial position. Say that again. There's one axial position, there's one equatorial position. The axial position may point up, as it does in this left top carbon. If the axial position points up, the equatorial position is going to point down, but not straight down. It's going to be in an equatorial position, but it will be down. Over here in this front carbon, the hydrogen in the axial position is going straight down. The equatorial position then is going up. So each carbon has a hydrogen going up relative to the carbon and down relative to the carbon. And one of those will be axial and one of those will be equatorial. Depending on the carbon, the equatorial position will be up or down, and the axial position will be up or down, but there will be one up position, one down position, one equatorial position, one axial position per carbon. Now let's consider the other structure over here and just make sure we can fill all that in. For reasons that I will get into in a moment, I'm going to put all of the axial positions in green. Now you'll see this might seem inconsistent, but you'll see why I'm doing this in a moment. So if the carbon points down, you put the axial position going down. If the carbon points up, you put the axial position going straight up. So we can decorate our molecule with all of these axial hydrogens, and then in the back here, put a little perspective. We can get a little fancy. So those are the axial positions. Now we're going to decorate the molecule with equatorial hydrogens as well. So here, that's going to come off of that position in that direction because it's going to be parallel to these two lines. I just started at an arbitrary position up in this corner. And there we have it. Now you might be wondering, why was I inconsistent here? On the left structure I put axial positions in blue, equatorial positions in green, where on the right structure I put the blue positions were equatorial, and the green positions were axial. Why would I introduce this inconsistency to the structure? Well, there was a reason behind that. It turns out that these two chair structures can interconvert. They are equilibrium structures that can interconvert into each other, and every position that is axial on this structure right here, every position that's, maybe just put a circle around it. Every position that is axial in this structure right here, after this chair flip process occurs, every position that's axial here will become equatorial in this structure. Every position that's equatorial over here will become axial in this structure. Okay, that was a lot to take in, and I ask you just to trust me that this thing called a chair flip interconverts the axial positions to equatorial positions and vice versa. Let me demonstrate how that works using a model. In this model, all of the green positions are equatorial, all of the blue positions are axial, and the chair flip process looks like this. Flip, flip, and take a look. All of the green bonds that used to be equatorial are now axial. All of the blue bonds that used to be axial are now equatorial. Then we can flip back to where we were before. There we go. And
flip again. And we can just keep flipping as much as we want over and over and over again. Now we're going to take a look at the energy diagram and look at each of those processes that are involved in a chair flip.
Let's draw a potential energy diagram of this process that through which the chairs flip. So draw a big graph here. And our axis on the left side will be potential energy, or relative potential energy. And the value for that will be kcals per mole. And our x-axis is something a little bit odd. We'll call it conformational coordinate. And we're going to begin right here. So we'll draw a little line there. That will be the 0 point, and that's going to be our chair. So we can draw our left chair structure from above. There it is, and I'll label that here as a chair. Okay, there it is. So now what's going to happen first is we could pick one of these sides. I'm going to pick the right side. This carbon right here is going to lift up a bit. It's going to lift up, and we're going to have a process that takes us all the way. Let me try to redraw that. Draw this a little bit clearer. It's going to go all the way up here and then back down. So what's up here at the very top? This carbon here is being lifted up, so we can keep the left side of the molecule looking the same. And now this is going to be kind of weird and over like that. Now remember, this is in the front, so we can put a little bit of a perspective there. It's kind of hard to draw, but it looks something like that. This is something called the half chair conformation. And it takes 10.8 kcals per mole of energy to reach that position. So that's a reasonably high amount of energy, but it's something that can happen extremely quickly at room temperature. So that's an energy value that we can easily accomplish at a very rapid rate at room temperature. Now, after this carbon has gone up here, this is like half the way up. It can continue, switch to red again. It can continue going up and get into a position down here to a lower energy conformation called the twist boat conformation. So we'll continue that to about here. Draw a valley. And this is right at about 5.5 kcals per mole. Put our little valley here. And let's draw that twist boat conformation. Put a nice solid line. Our carbon is now up here on this side. It's going to come down. Then we're going to have another bond in the back. Draw that a little bit. There we go. Make sure we can see that bond in the back. And then on this side, that carbon on the left side hasn't really changed yet. So that's called the twist boat. That's the twist boat conformation. Now we're going to go over another little hill. Not quite as high as the first hill. And this is what is going to be called, I don't like how I drew that. Make a nice bold line there. We're going to come up here, go down, and then cross in the back. Something like that. Made that a little bit too high. Let's go to there and then down. This is the conformation called the boat conformation. If you use your imagination, that kind of looks like a boat. And then you're going to come back around at this process, in this process. to get to another twist boat conformation, which we can draw like this. So hold on one second. It's just we're rocking back and forth from this twist boat to another twist boat, going through this boat conformation as a transition state in between those two twist boat conformations. So the other twist boat looks a lot like the first one. It's just going to be arranged in the other type of orientation. I'll show you what I mean here in a moment. There we go, something like that. So that's another twist boat conformation. And then at this point, we go back over the hill to get to another half chair conformation. So at this point, what's happening here is our left side is coming down. So the left side is going to be coming down. We're going to end up having this side being planar and flat. Draw that a little bit higher. Then the front will be coming out like this. It's kind of tricky to draw. There we go. We have our little kink there now. This is going to come up and down. There we have it. So that's our other half chair. Then as we continue down, we're going to get to our other chair conformation, which will have the same energy as where we began, but it'll be in the other format, where it looks like that. So just to be really clear about the center here, this valley of the boat, the energy of that, not valley, this hill, where we have our boat structure, that's at about 7.0 kcals per mole. A little bit higher than the twist boat. This does not go through a process where you have one twist boat, one boat, another twist boat, and then it goes over. Right here in the center, these twist boats and boat structures are just rocking back and forth. They just hang out there in that valley, rocking back and forth until they go over the other half chair and take us to the other chair form. So it's not like, just draw in that word chair. It's not like this is the only process through which this can happen. This whole area that's circled in red can rock back and forth many, many times before going over this hill. So this is our process, and these are the energetics that are involved in the chair flip process. Now we have to consider what happens when we have derivatives of cyclohexane. So derivatives of cyclohexane, let's just draw a cyclohexane derivative. We'll draw methyl cyclohexane, put a little CH3 there. Maybe put the line a little higher. There we go. So methyl cyclohexane, and let's draw a chair form of that structure. Don't like how that looks. See? Even people with a lot of experience can draw a bad chair form. And then we'll erase and redraw. Alright, I'm happy with that one. Now, this methyl group, note I've given it a solid wedged arrow to indicate it's coming out at us, although it certainly could be going away as well. We could use a dashed arrow, a dashed bond. It would be exactly the same structure. But I just wanted to make sure we remember that that's an sp3 hybridized carbon right here. So it's not going to be a trigonal planar geometry. Now, where could that methyl group go? You literally could put it anywhere as long as you put it in a correct position, either equatorial or axial. I'm just going to put it right here. So if we put it right in that position, now let's draw its chair flipped position. its chair flip structure. So we'll draw the other chair. And the question is, where is that methyl group going to be in this right structure? Let's begin by just labeling our carbon atoms. I'm going to call this carbon 1, 2, 3, 4, 5, 6. So we're labeling the carbon atoms of our cyclohexane ring. After this chair flip occurs, this is where carbon 1 ends up. So far left structure, carbon 1, is going to be the far left structure, carbon 1, far left carbon 1, will be the same. So whatever's on the far left will remain on the far left. Carbon 2 is now up there. Carbon 3, carbon 4, carbon 5, and carbon 6. So that is their new positions. Every carbon that used to point upwards is now pointing downwards, and so forth. So this methyl group, if it is at this position in the axial position, to begin, where will it be after a chair flip occurs? It must be equatorial. So it's going to be over here. It's still on carbon 1. It hasn't gone anywhere. It is here now in an equatorial position. Just keep labeling that blue. Abbreviated like that. So any group that's axial after a chair flip must be equatorial, and vice versa. So the chair flip process occurs here. That methyl group moves from axial to equatorial. But note something extremely important, and then I see students mess this up all the time. It's still going up. So the methyl group, relative to the center of the cyclohexane ring, still has an upward arrangement. It's upward axial, and it's upward equatorial. It does not switch to going down. If you begin up, you stay up. But you go from axial to equatorial, or from equatorial to axial. Let's look at this with a slightly more complex structure. Let's look at the structure of menthol. Okay, so let's draw here the structure of menthol, which is that compound that gives rise to a minty taste. It's in a lot of mint flavored things. So menthol is a cyclohexane derivative. There's a methyl group right here coming up. There is an alcohol over here coming up. And then down here, there's an isopropyl group. So that's our structure of menthol, excuse me. And let's draw our cyclohexane chair forms. Don't love how that's drawn. I'm going to just redraw that. That looks better. And we'll draw the equilibrium arrow here and draw the other chair form. Give a little bit of space. And there we have it. Okay, so now I'm going to ask you to decorate this cyclohexane with our methyl group, our alcohol, and our isopropyl group from menthol. Let's put those substituents on the molecule. What I'm going to do, I'm going to arbitrarily say, okay, our methyl group is here. Let's put the methyl group right here. If you want to put the CH3 here, that's fine. Okay, so I'm going to put the methyl group right here. In principle, we could have put that methyl group anywhere on the molecule. But if I put it here, now there's one specific place where all the other substituents must go. I'm going to ask you to pause the video, use a pencil, and try to draw out these two cyclohexane structures and indicate the position of the alcohol and of the isopropyl group. Pause the video, try to locate those positions, use a pencil, and come right back. Okay, I'm assuming that you have paused the video. Let's do this problem. We're going to put the alcohol and isopropyl groups on. So let's begin by numbering our cyclohexane. If that's position 1, that's position 2, that's position 3, that's position 4, that's position 5, and that's position 6. I went clockwise around the structure. That means this is going to be position 1, and you can maintain that clockwise assignment of numbers. So this will be carbon 2, carbon 3, carbon 4, carbon 5, and carbon 6 over here. So which position, carbon 3 it is, has the alcohol? So carbon 3 is the position that contains the alcohol. Now we have a solid wedge for our methyl group, and we're showing that methyl group going straight up in an axial position right here. We have a solid wedge for the alcohol. So where is that alcohol going to be? It's going to be on carbon 3, which is back here, and it's going to be up because it has the same relationship as the methyl group. And if it is up in that position, the up position on carbon 3 is going to be an axial position. If you want to, we don't need to put the hydrogen in. I'm going to put it in and then erase it. There's a hydrogen coming this way. That is not indicated in our line angle structure over here, and we don't need to indicate it over here as well, but I'm just showing it to indicate that it is going down. The equatorial position here is going down. The axial position is going up. I'm just going to erase that, but feel free to leave it in your structure. Now, where is the isopropyl group? That isopropyl group is on carbon 4, which is right over here on the other side. And if it's on carbon 4, it is going down. Its relative orientation compared to the methyl group, it's trans to the methyl group. So the methyl group is going straight up. The isopropyl group is going down. And if it's down at position 4, it must be axial. So that is our structure. That is our left chair structure of menthol. Let's now convert that structure of menthol into the chair flipped form over here on the right. Pause the video, try to do that. Put all those groups on in their correct orientations over here. And pause the video, try to figure that out and come right back. Okay, I'm assuming you paused the video and you've given it a good try. Let's begin just by labeling these carbon atoms. That's carbon 1, that's carbon 2, that's carbon 3, that's carbon 4, that's carbon 5, and that is carbon 6. Our methyl group is going up here in position 1, which is in an axial position. That means after the chair flip, it's still going up, but it's going to switch into an equatorial. I started drawing equatorial instead of the H3C. There we go. So it's in that position, in an equatorial position. Carbon 3 here is the location of our alcohol. Our alcohol is going up. It's going to continue to go up, but if it's going up in this position, it must be equatorial. So equatorial, it used to be axial, equatorial now. And then finally, carbon 4 is our home to the isopropyl group. It is going down. If it's going down at carbon 4 over here, it must be equatorial. So every position that's axial on the left side turns into equatorial on the right side in this particular example. So again, just reiterating this point, axial positions, any group that's in an axial position will convert to an equatorial position after a chair flip. If it began in the equatorial position, let's not forget, I'll put them in. Let's put them in green over here. We do have hydrogens. We drew them in earlier and I erased it, but let's just draw it in to remember that they are there. So these 3 hydrogens all began in equatorial positions. After the chair flip, this hydrogen here on carbon 1 is now going straight down in an axial position. This carbon 3 has the hydrogen going down in an equatorial position in our original structure to the left. That means it's going to be going straight down here in an axial position after chair flipping. And then finally, our carbon 4 has a hydrogen atom equatorial up in the original structure on the left, meaning on the structure on the right, it's going to be going straight up. So you can begin, if you begin in an axial position, after the chair flip, it's going to end up in an equatorial position. If you begin in an equatorial position, after a chair flip, you're going to end up in an axial position. But note the, for lack of a better way to say it, upness or downness of any of these substituents has not changed. The methyl group is going up on carbon 1. It is still going up on carbon 1. The alcohol is going up on carbon 3. It is still going up on carbon 3. The isopropyl group is going down on carbon 4, still going down on carbon 4. The hydrogens are going, this one's going down. Actually, carbon 1 and carbon 3 each have hydrogens going down, and they are again going down after undergoing the chair flip process. Carbon 4 has a hydrogen going up. It is still going up. The upness and downness does not change, but the axialness or equatorialness do during a chair flip. Finally, regarding these two structures, let's consider which one is more stable. So beginning up here with our methyl cyclohexane derivative, which one of these two forms do you predict to have lower energy? It might be difficult to see this at first. We'll look at another diagram next, but it turns out when you have an option between having a group in an axial position or in an equatorial position, having that group in an equatorial position is often, almost always, a more stable conformation. So we can draw that in here. More stable conformation. So the methyl group being in the equatorial position, it makes the molecule, makes the conformation more stable than when that methyl group's in an axial position. Down here in menthol, we have one conformation on the left in which all of those groups are put into, so the isopropyl group, the alcohol, and the methyl group are all in axial positions. After undergoing the chair flip, they all move over to equatorial positions. So in this case, we don't have to worry about a tug of war between different groups. Each one goes from axial to equatorial, and the position in which they're all equatorial will be the more stable conformation. Let's look at why this is the case next. Let's focus specifically on the case of the methyl group, and the principles we're about to see here apply to pretty much every other substituent that we might encounter, but the methyl group is a good one to begin with. So I'm just going to redraw our molecule of methyl cyclohexane in both chair forms. So that was the previous structure where we have the methyl group in an axial position, and then we'll put the structure over here where the methyl group is in an equatorial position. Now, consider this methyl group. It has some space, right? It occupies some space, and over here there are two hydrogen atoms. Now, there's a bit of debate exactly about what's happening here, or I shouldn't say debate, but it sometimes is taught that there's a steric interaction here that is causing a bit of destabilization. But it turns out that the methyl group is not quite big enough to have a steric interaction. But if we take a look at a model, we will see that there is another type of interaction that is present. So here is a model of methyl cyclohexane where the methyl group is in an axial position. And it's not exactly a steric interaction. You can see that there's some space here. Now, this is not drawn in a space-filling model. It's just drawn in a stick model. But the space between this hydrogen atom and these two, there's enough to actually accommodate that space. What's really going on here, I'll try to orient the molecule in a way that makes it easier to see, is that if we look down this bond, so we're taking these two carbons and looking right down that bond, you can imagine a Newman projection here that shows that these two carbons are arranged in a gauche relationship. Gauche relationships in butane cost about 0.9 kcals per mole of energy. So there's one gauche interaction here. There's a second gauche interaction if we look at it from the other side. Just wiggle it around to get it to view. There we go. There's a second gauche interaction. And if we consider butane, gauche interactions cost 0.9 kcals per mole, which I just said. Here we have two gauche interactions. 2 times 0.9 is 1.8. And it turns out that this energy, that this conformation right here, where the methyl group is in the axial position, is about, put a little tilde there, it's about 1.8 kcals per mole higher in energy. Than the compound, the molecule in which the methyl group is in an equatorial position. There's you can actually take a look at this effect for a variety of substituents. This value of 0.8 is what's called the A value. I'm not going to go into that in more detail in this introductory video, but every group could in principle have an A value, which is really just the difference in energy between a cyclohexane derivative with that molecule, with that substituent in an axial position versus in an equatorial position. So the higher the A value, the higher effective steric size of the substituent that you're considering. So the guiding principle for determining the most stable chair structure when you're looking at two chair forms that can interconvert via chair flips is you want to put the largest groups in the equatorial position. Largest groups in the equatorial position, that will be your guiding principle. Okay, well that concludes this video on cyclohexane chair conformations. I hope you enjoyed it. I hope you got something useful out of it, and I look forward to seeing you next time.